Hello, ladies and gentlemen. How we doing? It's me again. I know I'm upside down and beautiful. I'm going to go over the Reimann Sums. It's Friday afternoon, and I can't believe I'm doing this. But anyway, so you understand what this means. This is the left rectangular approximation. This is the right rectangular approximation method. That's all that means. So, rectangular approximation method is just how we find area under a curve using rectangles. Okay, MRAM is the midpoint rectangular approximation method. I'm probably not going to do much of that now, but these are all known as Reimann sums. Okay, they are a method of approximating the area under curves or for data using rectangles. The number of rectangles we divide a region into is called the number of partitions or subintervals. Doesn't matter; those two words are used interchangeably. In other words, if we break the region into 6 partitions, there'll be 6 rectangles, and later we're going to do trapezoids. Okay, so we're going to do, using the picture below, we're going to find LRAM, RRAM, and MRAM for each of these. Okay? Actually, I don't think we're going to, no, we're not going to do MRAM. We're going to do right, left, lower, and upper. Okay, so the left Reimann sum is the first one. I look at each rectangle, and it's defined by the y value on the left side. So my first rectangle is just this. So it's 8 units high, so not a good approximation. So it's 8 times 2 wide, plus if I go to the next one, the left side is 17 times 2 units wide. Next one is 19 times 2 units wide. The next one is 14 times 2 units wide. All these are 2 units wide. They're not all going to be always going to be uniform. The next one is 11 times 2 units wide. The next one is 12 times 2 units wide. And the last one is 20 times 2 units wide. Okay? And we would add those up. If I did those on the calculator, this is what, 16, 34, 38, 28, 22, 24, and 40. It's 50. Another 50 is 138, 178, 182, 92, 202. I think this is 202. So the left sum is 202. Okay? I'm not going to add the rest of them up after this. I'm just going to show you how to do it. Okay? The right sum, we're going to use the right side of each rectangle. So on this one, I'm now going to do 17 times 2. The next one's going to be 19 times 2. Then 14 times 2. Then 11 times 2. And 12 times 2, and 20 times 2, and the last one is 0 times 2. So this is a pretty crude way of finding the area under a curve. How do we get it better? We make more partitions, which then because if you look, if I go here, there's a huge amount of area. If I go here, there's smaller. Here, there's pretty big. Depends actually on the concavity. How much of your, or the steep, I'm sorry, how steep the line is in terms of your area. The error of it. Okay, so the lower Reimann sum now looks at each rectangle and takes the lowest number. Okay, it always takes the lower of the two. So in this case, it would be 8. So it would be 8 times 2. This one would be 17 times 2. This one would be now this side, which is plus 14 times 2. Now I take this one, would be 11 times 2. Go to this one, it's again 11 times 2. Go to this one, it's 12 times 2. And go to the last one, it's 0 times 2. The lower Reimann sum is the least it could be with this number of partitions. And the last one, the upper, is definitely the highest. And then these two, if you line up the sums, these two would fall in between these two. Okay? All right, so now the last one, we're going to do the upper, as what I heard in college, the TA I had said upper sum. That's the upper sum. But anyway, that's something I always remember when we get to these. So just a little joke. So if you look at these two, the biggest of these two is 17, and it's 2 units wide. This is 19 times 2 units wide. I go here, and it's 19 again. I go here, it's 14 times 2. I go the next one, the y value, biggest y value is 12 times 2. And then this one is 20 times 2. And then the last one is 20 times 2. You know, really what we're doing for each of these, you're drawing all these rectangles for each of them. Okay? If I drew them at each one of these, I draw the high one, I draw the low one, I draw the high one and draw the low one, draw the low one and draw the high one, and then I draw the high one, and then the low one is actually down here. So those are all the rectangles. So the left one uses this one, this one, this one, this one, this one, this one, and this one. The right one uses the big, the small here, the small one, the bigger one here, the bigger one here, and the smaller one. The upper takes all the big ones, and the lower takes all the small ones. Because that's really what we're doing. We're approximating using rectangles. So it is crude, but when you have data, you really don't have a lot of choice because we don't know. We will eventually do trapezoids, which if you look at it, will significantly reduce our amount of error. Okay? All right. So we did those two. Now we're gonna space it out on the next one. And now, if you look, these are not uniform anymore. Okay? We're gonna do the left, right, and upper. So now if you look at these, this one is 4 units wide. This is 2 units wide. This is 6, and this is 2. So we're going to go about the same way, but our if you look, it's wider, so it's actually more imprecise. We're introducing bigger error. So if I look at my left sum, the left one of these two is 8, and its width is 4. Look at these two, my left one is 19, and that's times 2. This one is, my left is 14 times 6. And this one is, the left one is 20 times 2. Okay, I would normally add all those up, and I would expect you to add all those up. This is 32 and 38, and that's 84, and that's 40, so it's 124, 156, 66, 76, 86, 94. So this is 194. All right, so let's go do the right ram. Boy, I probably made a mistake on that one. But anyway, let's do the right ram. So if I look at these two, my right side is 19 times 4 plus my right side is 14 times 2. And then my right side is 20 times 2. And then the last one is 0. I'm sorry, it's 20 times 6. And then the last one is 0 times 2. So the right one uses these, the left one uses, those. So anyway, and the upper is the extreme maximum the area could be based on these intervals. So this is going to be 19 times 4. The biggest of these two, again, is 19 times 2. The biggest of these two is 20 times 6. The biggest of these two is 20 times 0. Or no, 20 times 2. So that's an example of Reimann sums. That's given a graph. Now I want to do one from an equation, which is actually find the area under a curve. Now we're going to talk a little bit about this, how you can also look at it a little bit differently. All right, so I'm going to look at 9 minus x squared on the interval of -1 to 3 with 8 partitions, subdivisions. I've kind of stretched this out because this is -1, 0, 1, 2, and 3. And 9x squared is going to be way up there. I'm going to call that 9. And I know my graph looks something like this, and at 3 it's 0. So here is our area. But we're going to divide it up into 8 rectangles. But I'm just going to give you a picture of it, but we're going to work off of a table this time instead. Okay? So if we are doing these are going every half unit. One way to look at with 8 partitions, how wide is each one? You do 3 minus -1 divided by the number of partitions. So that's 4/8, so it's a half. Okay? So we're going to do our x values are -1/2, -1, or -1, -1/2, 0, 1/2, 1, 1.5, I'll go to decimal land, 2, 2.5, and 3. So those are our values. Okay. The simplest way with a calculator would be to go to your table. So I was already prepared and set this up. Okay. And if I go to my table, I think I'm set up, yeah, so my delta x is 1, so we need to go to setup. And you can either go second table set, or you can, when you're in the table, you can hit F2. And our table is starting at -1, so I'm going to type in -1. The big thing is our change in table needs to be 0.5. Okay? Now to make sure that I'm saving what I did, I have to hit enter. And then enter again. And now it adjusted so it did each one of those. So my y values are 8. So I'm just going to copy those down. 6.7, no, I'm sorry. No, this is 8. At -1/2, it's 8.75. And then 9. And then 8.75. And then at 1... down. At 1 it's 8 again, and then it's 6.75, and then it's 5, and then it's 2.75, and then it's 0. Okay? So we're going to do left RAM, and I'm just going to look at the y value. So if we agree, these are all the same width. So, okay. So the left, if I look at each of these, I'm going to take each of these 2 y values, and I'm going to take, the left is always going to be the one above. So I'm going to use 8 times 1/2. Now I look at these 2, it's going to be plus 8.75 times 1/2. And then it's going to be plus 9 times 1/2. Then it's going to be 8.75 times 1/2. Then it's going to be 8 times 1/2. Then it's 6.75 times 1/2. Then it is 5 times 1/2. And lastly, it's going to be plus 2.75 times 1/2. And that was our LRAM. Okay? And if I did my right RAM, which is the last one, I'm now going to take the right side of both of those. If you think about it on this region here, it's always going to be starting with this one. So that's going to be all of these, if you really think about it, plus the last one. Okay, so that's going to be 8.75 times 1/2 plus 9 times 1/2 plus 8.75 times 1/2 plus 8 times 1/2. Ooh, I'm off the page. Some would say I'm off the wall. Plus 6.75 times 1/2 plus 5 times 1/2 plus 2.75 times 1/2, and then it's plus 0 times 1/2. Okay. The other thing I want to make a comment on, so that would give us our left RAM and our right RAM. But what I want to make a comment about is, what if this was velocity? Okay? And if we have velocity, my units would be feet per second. Yeah, the bus is out front.
The bus is out in front.
Anyway,
Going to Elk
so
Grove.
that's at feet per second. And if the y value is at feet per second, and this is in seconds, so it's just a velocity curve. Well, what does the area under there represent? the area under that curve, if you just do a unit analysis, would be feet per second times seconds, which gives me what? Feet. So what does that tell us? The area under the velocity curve is actually the distance we travel. So if this was the graph of the velocity, and we computed the area under that curve, the left RAM would give us an approximation for the distance traveled. The right RAM would give us another approximation for the distance traveled. So that's really the direction we're going is we're going to get into area and how we compute areas. How do we get better approximations? We do more rectangles, or we increase the number of partitions. Eventually, we reduce our error more and more and more, and there's a way we can get the exact area under there, and that's the direction we're going. So this was our introduction to Reimann Sums. You should be able to do the values under there, so they do give you velocity or position and velocity, time and velocity. The area under there would just be the distance traveled, so you could easily do that also. But anyway, hope you have a nice weekend, and that's all, folks.